transmission electron microscopy because it is a method which is so extensively used today. And what we can see here in the top, we have in this type of electron microscope, in any electron microscope, we have a light instead of light that is used in light microscope. We have a beam of electron which is high energy. And the high energy will pass through the sample which is located here. You have a series of condenser lenses, and then essentially you get the light that is passing through your object, and you can use it as an analogy to shadow that I have shown previously. However, here this is why the light is transmitting through the sample. It's a transmission electron microscopy. The problem with transmission electron microscopy I have some issue to make it full screen. Yes. The issue with the transmission because transmission electron microscopy gives us very high resolution. Today we can routinely see objects which is like 4 million times higher magnification than we can see in naked eye. We can get very fine details, we can get internal structural detail, that because the light is passing through, the electron beam is passing through, we can see individual atoms, and we can get the morphology, how a given nanoparticle looks like, we can get atomic level details, we can get much more, and it's the only microscopy technique where we can do entire elemental mapping, we can do spectroscopy in situ in real time. And there is no other microscopy technique that can do at this resolution. But there are limitations for this. The limitation is that the sample should be thin enough to obtain very meaningful results. And if it is not a problem, the thickness of the sample, because the electron has to pass through the sample to get a meaningful result. So the higher thickness is about 100 nanometer. Sample should be mechanically robust because we use high vacuum. And that not all samples meet above criteria. That's why there are very different types of sample preparation. Let me give you one example. If you have a spherical particle or a disc and rods all oriented in this way, and we think that the light is electron beam is coming through. If you take a 2D, the transmission image, which is essentially 2D projection, they all will look similar. And that means the conventional electron microscope images, they represented 2D projections of 3-dimensional object. Now if I slightly rotate these objects, then you start to see the difference, then we can distinguish if the particle is really a disc or a rod. So the idea is that this 2D projection depends on the orientation of the object. So we can summarize that 2D projection is in TM depends on the orientation of object. 2D projections also contain a lot of internal structural detail, but we are not able to extract because they have overlapping information. Then how to get this done? Let's say here is an example in the left side with the red circle that I have shown. These are DNA origami and designer DNA structures. They have a rectangular structure, but here you can see some outliers. But they are same structure, they are standing upright. Then we have different kind of structure. Here cylindrical structures, they have different in their cell and the core. In one case, the core is light, it has high contrast to the cell, a uniform core cell, and you see some pattern. Now, how to understand and how to get what these structures are really are. And that's long ago, in 1960s, Roser and Klug, who also got Nobel Prize, proposed principles how to construct 3-dimensional structure from 2D projections of object. And this is called 3D reconstruction because you have in TM image 2D projections of 3D objects. So you are able to construct by connecting many images. And how it's done, I have shown in an image in the beginning of the transmission electron microscopy. It looks like and here is real sample electron beam that goes through. And today we have more advanced cameras, so we can image, we can get the digital image. We have the sample tracing extremely small 3 millimeter sample grade, and because we have to get images in different angles, we rotate this goniometer. So as you see, when you rotate the object here, it will change its shape, and it's not that it's a different object, same object. The moment you look at different angle, you start to get different image. So this is called a series of images that you collect. So this is also called tomography. It is nothing but constructing a higher dimensional structure from a series of lower dimensional projections or images. When I say higher dimension, if my images are 2 dimensions, you combine all of them, you can construct a 3-dimensional image. So that's why it is called 3D electron images. So tomography and 3D reconstruction, 3D electron image, they are one and the same, used interchangeably. How we have an object and then we collect a series of images with an increment angle. We have images because if you did more than this, it blocks the electron beam, so we cannot collect. So at this stage, there are different images. This is the total projection of an object that we see. Here, we collect about 70 images with an increment angle. There will be some processing and reconstruction. And from this, what we can do is that collect all of them, stitch them together, and then it looks like an object is rotating. It's actually not. It is necessarily we are tilting the sample grade. Once we have this, there is a more mathematical reconstruction which utilizes certain amount of computational resources, and then you can color them artificially. Here red means strong red means high contrast, something like that. And then you also have low contrast elements, organic. This case is a nanoparticle coated with the peptide. And you can also do a cross section and you can identify individual nanoparticle location. You also get an idea how it looks like. So essentially you use tomography or 3D electron microscopy is a combination of imaging and image processing technique. I give now a couple of examples how it helps us to understand the structure. Here is a very simple chemistry. We have a cobalt octacarbon and we treat it with some amine terminated ligands. In this case, parabenzoic acid. It results in nanoparticle and is spontaneously assembled because of the hydrogen bonding between the ligand into higher order structure. And we see 2 types of population. The one which has a difference in the core and the cell clearly defined, the other there is no difference. Now if you look at the electron microscopy and 3D reconstruction, we see that this has a multilayered cell and it is an empty core. That's not all. So we get an idea how the structure looks like. It's a spherical. We get internal structure detail. We can get individual packing pattern. That means how individual nanoparticles are arranged. From these, we can collect similarly looking or size and shape nanoparticle, which is called subtomogram, and we can say how a single nanoparticle looks like. Such complex structures, we are able to identify the ways and position of the structures. And we can go on what is there's little difference except that material has LSS material. These are spectroscopy. It is so that it is simply the organic ligand that are in excess that trapped inside structures. Everything else remains the same. We can also see some reaction between different types of nanoparticles. Here is gold nano, which has a cationic head. And you can exchange these ligands because they are not covalent. It is some different types of ligand, is carboxylic acid. Now we have, there is little change in the shape and size because the ligand is extending to the surface. Now, if you can treat with another type of small nanoparticle, which are molecularly precise, which are similar as carboxylic acid, we can get some kind of product here. And this is not that exciting, but what's interesting is that we have this type of structure, each of them encapsulated a single rod. And that is because the reaction between two types of particles is molecularly precise or atomically precise clusters which have the same type of ligands and the surface is same. To understand how this is the structure, let me this projections quickly you can understand. And you can do the reconstruction image. What you see is an house. Page, and each page has one nanorow inside. You can look at the cross section and see that how the rod is arranged. It's a simple way to encapsulate one nanorow inside a cage without any complex design. And this is the simplest way. But now, why there is only one rod? Why it is octahedral structure formed? For that we need to gain more understanding. And a nanorod behaves like an exchange as its kind of that way. And then understanding from the model of the exchange as we change the ligands of the surface. And what we also do is certain changes of these nanorods, and which actually suggests that why there is a larger growth on this area rather than on the edge. So it is not time independent image that we could propose the mechanism of the structure. What we saw here is that in the beginning we can say how to similar structures are different and why they are different. Then we can also show that how we can devise a mechanism of large metabolism. As the beginning they said that it is highly interdisciplinary. As they move on, I covered from microscopy to nanoparticle, organic, now I go bio and inorganic hybrid materials. We have whole nanoparticles, which are cationic, which have very narrow size dispersivity, which are water dispersible, which means that they are stable in active solution. And here is a surface plasma resonance spectra of this, which has an indication that nanoparticles stable. In the aggregate, you start to see some change. So even 20 hours into temperature is stable because they are highly charged in every superconductor. Then we take virus particle. These are not harmful viruses. These are tobacco-mosaic viruses grown in tobacco leaves, which have about 300 nanometer in length and about 80 nanometer in diameter. The surface charge here is negative. It's a natural colloidal nanoparticle with surface charge negative. So now we have a gold which is spherical. This is anisotropic rod-like particle. If you have a surface charge cationic, you can aggregate and disassemble them by adding some electrolytes because it screens charge. If you add some sodium chloride, any other electrolyte, you can increase the adding and aggregate. If you dilute now, add more water to this, you can go back to the particle. This concept can be used for comparing parts. Here we have a semantic representation. We have this type of aggregates, and then we add tobacco virus. Then we decrease the ionic strength, which is called as dialysis. So the salt is concentration is increasing with time. Then individual particles start to come out, and then we start to get this. We can also visually see, like by changing the ratio of cool and EMP, at certain rates we start to see they start to separate, and this is because a large micrometer or millimeter structures are formed. And then you can take small X-ray scattering, you can monitor what we see is that there is a clear diffraction makes electric scattering helps you to study in situ in limited state if there is any nice order structure formation. And we also identify at what concentration a good structure is formed. Then we can go on and look into some of the selected samples at different ratio. Electron microscopy, when we mix them, you see nanoparticles here. There are certain individual recombinant virus particles. That means that this kind of structure is observed irrespective of the concentration. But there are uncomplex structures are there. We also noticed that the initial structure formation, for that we need more concentration dependent. As you increase the concentration of food, we start to see the particles tend to go in a specific place and form. So here it is a trialectron microscope. And this is because a process what we call as a zipper mechanism, where initially a nanoparticle goes and binds and then brings together two virus particles and then it creates an electrostatic potential. So the next nanoparticle has a reference from the place where the previous nanoparticle is at. It will not randomly move and the same like this. So that's why we call it as a zipper mechanism. We have said that we have seen small and X-ray scattering, but small and X-ray scattering gives no idea why we observe such specific peaks. In physics, if you take a rod-like particles, it always forms an hexagonal assembly. But small and X-ray suggested that we have a square lattice, something like this. But in the little, you can explain why there is a dimensional lattice and why we have a square lattice. Because it is not following the principles how it is typically observed in the literature. So the only way is to look at 3D structure. So this is structure which is of the micron length.
Number of participants is screenshot.
And then what we see is that also some chemical structures. If you do an electron tomography, here you only see but not virus rods, because virus have a different contrast. Therefore, it is not possible to get both of them simultaneously. So we can do more colorful artificially colored structure, and then what we see is that there is a light and a helical structure that gives information about morphology. But what we can also do is that we can identify every location of every nanoparticle. Then do this more calculation of the spaces between each nanoparticle where the virus is actually occupied. This says that this is a size dependent. And all these coordinates can be used for simulation. So we can use any information which data. So we can reverse engineer. Now we can take the data between smaller size particle instead of a size of what we have used.
Yes, sir.
So that is, it provides a provides support for small and X-ray observation and support, for example, computational simulation and also design. Here we show that how the nanoparticle virus rod-like structure is dependent on the size of the nanoparticle. If the smaller nanoparticle, then of course the difference is bigger, then it gets smaller. We can use variety of other nanoparticles like delphins and long tail, which are like highly flexible nanoparticle surfaces. This helps us to understand, and then we are able, for example, in this case, we can change the rod size. Then we use an algorithm called we can change the rod square plate-like structure. We can develop a variety of matrix and create a more kind of variety of superstructures with a different morphology. So the idea is that if you want to solve a three-dimensional structure, it helps you not only to understand but also generate a structure of your choice. So now you know what type of nanoparticles what type of organic structures by changing this, you can predict how test cases may be. So electron tomography also has limitations because it depends on the thickness, as I said. If we tip the sample, also it increases the brightness also at a larger distance. So artificially it increases the thickness, then it's difficult to focus or because collect also a large number of images. It also damages the sample. We have to focus and leave color as high. But not all samples is convenient. Now, what about the resolution? Ideal resolution is if you want to put a lot of images. There is an old equation. However, this is not valid. It's only valid for spherical structure. It depends on the diameter and number of the projects, diameter of the object. If you have a object of 200 nanometer, you have 70 plus 70 minus 70 at the angle of 2 degree, you will have 140 images. Then 70 images. Then it is possible that you can get a resolution of 8.9 nanometer. That means the objects of this distance can be visualized clearly. But sometimes, here I am showing one object. This is a protein-based pulsar base, which mostly has liquid. But still, what I am showing is that in this image we cannot get any idea. It is a deformed because of the water when you dry it in the hospitals. But if you do tomography and cross-section, what you see is that even the protein has less than 10 nanometer resolution. Where we can identify individual protein layers and individual components. So I always say that it's possible that tomograms can often be copied, so we can get more details. This is what I've been doing, but here there are many tools working on even more advanced. If you're working in catalysis, what's called atomic resolution tomography, where you have individual particles, individual atoms can be seen. So you can do some defect location catalysis, and this is a group in the States. John Young, he works on atomic resolution tomography. More advanced technicals coming, which are becoming routine soon, are microelectron diffraction. Slightly different. You can use, if you have a small nanoparticle, then you can directly use by electron diffraction method. So the advances are going rapidly, and it is becoming routine in medical and even pharmaceutical application to study co-crystals which cannot be grown into bigger crystals. Proteins are routine study protein drug complexes. So what I can summarize is that transmission electron microscopy gives the projections in conventional imaging, but we can only get limited information. Electron tomography offers us a numerous opportunity to study self-assembly mechanism, morphology, internal structure, provides useful data for computation simulation. It is a complementary tool for many other analytical analysis. With this, I stop the scientific. I will take 2 slides to look at where I am from. As Debrina said, that I studied in Bangalore, but I was born and brought up also in Karnataka state. I moved to Finland many years ago, once during my PhD also. Then initially I was around central Finland. It is then I moved to Helsinki. Now I am located in Tampere University, which is also central or west Finland. Small city of maybe 300,000 or 1,000 people. But the beauty here is that the whole city is surrounded by lake. But now these are all frozen because of the winter. Our university is not new. It is close to 100 years old, but recently formed, combining 3 different universities in Tampere. It's a foundation based. Now we have 5,000 staff, 20,000 students, 7 different faculty. I belong to Faculty of Engineering and Natural Sciences. Within that, we have different units, and I am in one of the sub-units. And this is the entrance of our main campus. We have multiple campus, and this happens during the 1st of May, where students have some celebration. This is the scene that you will see in the summer. With this, I would like to stop now, and I'm happy to take any questions.
Thank you, Dr. Nanappa. May I ask the students to ask questions? Actually, they have already posted some questions. So, Protein Chakraborty asked, do nanoparticles show color?
Okay. In general, yes, nanoparticle of course has color. Debrina knows this very well. You worked a lot. It depends on the size, shape, composition. Nanoparticle can be luminescent when you go to this molecularly precise. And in one of the slides, you saw virus. These complexes, yes, they have that color typical of gold, and that color you can also understand why, because the surface plasmon is in that region, so visible region. So the color can be tuned. That's also the beauty, depending on the composition.
The second question is from Shudeep Mandal. What is the difference between superlattice and normal lattice?
Yes, superlattice has two or more than two components. In this case, what I have shown is like a virus and nanoparticles, but they have a very well defined lattice structure, and this lattice is coming from higher order. So it is kind of a self-assembled, supramolecularly assembled structure, and it's, it is. Normal lattice, what you talk about, the atomic arrangement on a given and a simple molecule or metal, so that makes the difference here. Length scale and the number of components.
Okay, the next question is from Shontu Haldar. What is the application of nanoparticles in today's life?
Yeah, because nanoparticle has so many types. So there are metal nanoparticles, there are organic, there is lipid. So you all have taken vaccines. If it's Pfizer based, or then it was lipid nanoparticles were used to encapsulate and stabilize. And we have heard also in the morning in the inaugural speech that how a nanoparticle based drug was helping for cough. But in metal nanoparticles, a long story. Um, um, Olden days, it was, if you take, it was used in a lot of paints, which is even today are so stable. But the composition and documentation is not available. But they are all like many gold, silver, and copper. This combination. And then the next application came like in 70s, 60s, that immunogold, extensively used in biology, is to label specifically some specific cell, which was used in TM, and those golds are so stable for imaging, and they are very important because biological samples don't have enough. And these are small molecular clusters of at that time, immunolabeling. And now, yeah, it is depending on the type of nanoparticle. We cannot say that what we do can be directly used,
এখন সাউন্ডের
say,
ফিডব্যাক
for
আসছে
health related, but it can be for imaging, it can be for optics devices. Yeah, depends on the application, and the application depends on the type and composition and the property of nanoparticle. So it's a wide,
কি হচ্ছে
yeah.
So next question is from Rama Mandal. Actually, she asked the
Maji
same
आवाज হচ্ছে?
question.
Yeah, yes.
Students collects. Okay. So any other question from students, faculties, anyone? Any other
Yes, there is one question. What do you mean by cross-link connection among
TMP and gold number?
Yeah, there is no chemical covalent bonding. It's just because one surface is positive, another is negative. So there is, if you just simply add positive and negative, you get an aggregate. You cannot get an ordered structure. So what we do is at a controlled structure formation, where you release one of the charges slowly, like the nanoparticles, step by step. That way you can control the structure, because when the particle interact with one, it creates an electrostatic potential, and that attracts the next cationic particle coming. So it's purely an electrostatic interaction, which you can control by changing the electrolyte concentration. Yeah.
Any more questions? Okay, let's thank Dr. Nagpal. So you have spent your valuable time and given a nice lecture. I'm sure we all will benefit from this. Thank you once again. I hope that we will again get you.
Yes, thank you. Because I was not sure about the audience and the level of understanding, and I'll be happy to give more detail if needed and priority on this type of topics. That routinely what I teach.
I think this cryo TEM is very much like new to them, because now they have an idea about TEM, but they don't have that idea about cryo TEM, and they don't know certainly about the 3D projection. Like mostly they have seen the pictures and the regular TEM images like from the research papers. But so actually students are asking me in WhatsApp that what is this 2D to 3D kind of things. So certainly they are excited to know about all this. So thanks once again.
No problem. You're welcome.
Thank
Thank you. Thank you.
Thank you.
you.
So let me introduce our next speaker. She is Dr. Shreyoshi Chattopadhyay. Shreyoshi joined Professor John Irving's group as postdoctoral researcher in November 2018. She completed her bachelor's and master's in chemistry from Jadavpur University. Shreyoshi pursued her PhD research under Dr. Gautam De in CSIR Central Glass and Ceramic Research Institute, and received her doctorate degree in May 2018 from Jadavpur University, and then she moved to St. Andrews, UK. She became a member of the Royal Society of Chemistry in 2020. She is serving as a reviewer of several reputed journals. She was recognized with one of the Best Reviewer Awards from Materials Advances and RSC Advances. The objective of her research is to develop new hierarchical nanostructured and emergent nanomaterials and to exploit them for energy applications, mainly in the field of photo and electrophoresis. Now I would like to request Dr. Shreyoshi to deliver her talk. Thank you, Devinadi, for your introduction, because it's too much exciting for me as I would like to say Devinadi was my senior in my PhD lab, so it's really exciting for me. And thanks to principal and the organizing committee for inviting me and giving me the chance to share some of like the research here. Hope I will meet the expectation. Let me share the screen. Is it visible? Yes, it is. Okay. Yeah. It's part now. Good morning, everyone. I'm Shreyashi. So today my topic is nanomaterials for green hydrogen production. Someone was asking like what is the application of nanoparticles, but like here I'm going to talk about application of nanomaterials, how we can use it for green hydrogen production, like which is just putting water to make hydrogen. And maybe some of you are aware that hydrogen is going to be our next like fuel in near future. But before going to my talk, I would like to say something about St. Andrews and how I came here. So, as Debinadi said, after PhD, I moved like 8,000 kilometers away from my home to UK for postdoctoral research in St. Andrews, which is a very beautiful place, and it's it's in a coastal region near North Sea, and you can feel like
very beautiful season change from summer to winter. And sometime if you are lucky, you can have a chance to see northern lights. So this photo actually I have taken a few weeks before. Sorry, let me. Yeah, so few weeks before, like I got the chance to see the northern lights here. So it's basically a beautiful place. Now, coming more in detail to the university, St. Andrews is a very old university. It's like more than 600 years old and is the oldest university in Scotland. And another iconic place is like the golf course, because Scotland is famous for golf. And the golf course here, which is like called Old Course, is the oldest golf course in the world. So you can imagine how important this golf course is for the golfers. So this is really nice to be here to explore all these things. And next is talking about the Department of Chemistry, which is also very old. Because if I am remembering correctly, like the professorship in chemistry started from Germany in the year of 1608, and from St. Andrews they started since 1808. So it's you can imagine how old this department is. And there are several groups working on a variety of research field. Some of them I just tried to jot down in this slide, and you can see groups are working from organic to materials, chemistry, biology, interface, energy, environment, and several functional materials as well. So I just tried to put some links. If you are interested, you can just go and see how the research is going on in this university. You might have some ideas about the research topic and the materials and all those fields. So now let's talk about research. So like I tried to make this presentation very simple. So research in my thought is not a single word. It's presenting a cluster of words, including idea, success, trials, failure, thoughts, and like much more. So how we do the research? So first, what we do, we choose a topic, research topic that seems to be interesting for me or who is going to do the research. And then we do some literature survey to fix our aim or hypothesis, and to know like what is the current status of that particular research topic. And depending on that, we try to select some methods. Like particularly for chemistry, I can tell we choose some methods to prepare some materials, as Dr. Bonappa was also saying about preparing materials, how changing the methods can change the structure, size, and properties of the materials. So depending on like the aim, we select some methods to prepare our material. So once we have our material, then we go for characterization of those materials and collect some data. So this is not the end of the research. Now we have to analyze those data to interpret what is happening, or like why this kind of data we are having. So we analyze those data to reach to a conclusion. So basically, if you see this diagram, you can understand research is not a single task, is a like task that depend on several steps. Now, as I told, like first you have to choose the motivation or like the research topic. uh, so for my research area, I'm working on nanomaterials and exploiting them for green energy. So if you see today's title of this talk, you can like ask, what is the motivation of this kind of work? I'm not going to discuss about nanomaterials, because now I think most of you started understanding why nanomaterials are so important for today's research. So next, going for the green hydrogen. So main motivation for green hydrogen is world fuel crisis and climate crisis. So how it's happening? It's happening from use of fossil fuels, because we all know fossil fuels are very limited, and depending on the energy use, it might be finishing soon. So we have to think about any alternative. So this like extensive use of fossil fuel is actually creating world fuel crisis. And also, not only that, when we are using fossil fuel, like during running cars or different kind of vehicles, we are producing this kind of greenhouse gases like carbon monoxide, carbon dioxide, nitrogen oxide in different forms. So those are basically polluting our environment. And what is the result? So this is actually increasing the temperature of the earth, which, like, I think all of us now know what is going on in the polar region, and even all over the world, like say, increasing temperature. So basically all these are interconnected. So this is the motivation of the work. So what is next? Now we have to think about alternative energy. What is that? This is hydrogen. Hydrogen is a very environment friendly fuel, and now the research on hydrogen fuel is very emerging. Like many research groups all over the world are trying to produce hydrogen in different way. Why? Because we can produce hydrogen simply from water, which is not very easy, but it's doable. We can make it. And when you're using hydrogen, it produces only water, which is also not harming our environment. That means hydrogen is a good fuel to use for the future to protect our earth. Now, coming to the spectrum, because many times maybe I use the term green hydrogen, but we all know gas, like hydrogen doesn't have any like color. So from where it's coming? So this slide shows 7 colors of hydrogen, which is basically coming from the process of producing hydrogen and the greenhouse gas emission during production of that particular hydrogen. So if I talk about black or brown hydrogen, you can see it can be produced from coal via gasification. But during production of this hydrogen, it can emit a huge amount of greenhouse gas, which is not good for our environment. That's why it's categorized as black or brown hydrogen. And depending on this greenhouse gas emission level, it divided in colors. Now, if I come to green hydrogen, you can see it's forming minimal amount of or even sometimes no greenhouse gas. And what is the process? So we are simply doing electrolysis of water. Either like you can use these energy sources like wind, solar, hydro, or thermal energy to produce electricity and split water, or simply you can use solar energy to split water to make hydrogen. That means it's very green. It's not damaging our environment. And what is the current status of this green hydrogen production? So if you read some news, you might know India has already launched one 32-seater bus, which is running with hydrogen fuel cell. And this bus is this can run until 450 kilometers by utilizing 30 kgs of hydrogen. And also hydrogen powered vehicles are, if you compare because nowadays people are also thinking about battery powered vehicles. So if I compare battery powered vehicles with hydrogen powered vehicles, so hydrogen powered vehicles are little beneficial depending on the cost and also refueling time, because it takes only 3 to 5 minutes to refuel like the tank. And with a single tank, you can run 350 to 400 miles. So it's useful. And since we know India is third most attractive country for renewable energy, so like severe effort is given to make like green hydrogen and to make the target as well. So India government has set one target that by 2035, 30% of fossil fuel in the refineries needs to be replaced by green hydrogen. And another point is, if you are not aware, for the fertilizer production, the main constituent is ammonia. So that production of ammonia is also needing hydrogen. So another target is set that 70% of fertilizer production should become from green hydrogen by 2035. Therefore, like the main target is to make 5 metric ton of green hydrogen by 2030. So you can understand how important this research field is. Now, how we can make the hydrogen by only like photocatalysis? So basically, photocatalysis is splitting water using light energy and making hydrogen and oxygen. And how it works? So, like valence band has electron, and if you irradiate the same material with light, then electron from valence band can excite it to the conduction band, and this electron can take part to make hydrogen, whereas the hole here can take part to make oxygen. So which kind of material are suitable for this kind of application? We need to choose some semiconductor materials, mainly transition metal oxides, sulfides, or nitrides, and they need some proper alignment of the bands while using for this photocatalytic application. And sometime for making like hydrogen, we use some sacrificial agent like in terms of like methanol, ethanol, IPA to block this reaction and to only to produce hydrogen. And all these started in 1972 when Professor Fujishima and Honda was studying some photoelectrocatalytic work with their TiO2 coated thin film. They observed that when they are irradiating the film, it's producing some gas which is hydrogen. So since then, people are trying to modify their materials like by concept of structure or aligning the band to get very efficient photocatalyst. And here in this slide shows some like example of those kind of photocatalysts that nowadays people are trying to modify or work on to get very to make it like efficient. And the most important is TiO2, and some of them like you might see on your like on how to say ingredient part of your sunscreen lotion as well, if you check carefully the ingredients of your sunscreen lotion. Now coming back to the research part. So we need to make the material. So for this purpose we use the sorbothermal technique, where we mix the solution and put them in autoclave and put that autoclave in a like a oven and let them to react to make the product. But if you are wanting to make some fibers, you might use electrospinning instrument or deep coater for making thin film. But at some point you need to use muffle furnace. And when you have your material, then you need to characterize those materials by using some tools. Like some of them are very familiar to you, like UVVs or IR, even Raman and XRD as well. So Raman and XRD are mainly used to characterize the structure or like phase of the material we synthesized. Sometimes like FTIR is also used to know about the functional groups present on the surface and the like the structure of a material as well. But for this photocatalysis application, UVVs is a very important tool to characterize the material. I will come later how we use UVVs. And we like this morning session we like learn about electron microscopy, how we are exploiting electron microscopy to understand the structure of our nanomaterials. So these all characterization units are used to understand the material we produce. After that, we go for catalytic application. So this is the photocatalysis reactor that I'm using here for making hydrogen. So what we do, what is this? This is the system that is used for photocatalytic experiment, and this is connected to on in situ GC, which is gas chromatography, which tells us about what kind of gas we are producing and how much gas we are producing. So this unit is also very important to know your gas and the amount. So how it works? So there is a like a reactor where we use the solution and the catalyst and irradiate with the lamp. Here you can see, and then let the reaction like happens for some certain time, and then collect the gas to analyze on GC. So these are some experimental conditions that we are using, because we are using a xenon lamp that has like from UV to IR range like lights wavelength. But if someone wants to like work on visible range, then they can use some filter which is removing light below 400 or 420 nanometers, so that they can work under visible light. So we like since solar light has maximum like visible light and UV light is I think only 4%. So people are trying to make some catalysts that are active under visible light. Now coming to some work. So for this work, if you see, I tried to make some like structured TiO2 nanomaterials. So these are this is of micron size, but if you see the see it under TEM, then you can see these structures are actually formed with some small nanoparticles. So depending on, if you see, depending on the solvent, while I was doing some solvothermal, it made some different structure. So it ended up with some cuboidal structure and also some spherical structure. So this is a 3D hierarchical TiO2 structure. And for the example B, what we were trying to do, we were trying to make some nanofibers that has gold silver nanoparticles forming the alloy. So how do we know it's making alloy, or it's like just making some silver nanoparticles and gold nanoparticles? So for that reason, we do EDS mapping, elemental mapping, to see how the elements are distributed all over the structure. So if you see this part, this is normal image. And if we go for the elements, you can see this has Ti and oxygen that is coming from TiO2. And for the nanoparticles, you can see for this single nanoparticle, it has both gold and silver. That means this nanoparticle is making alloy. And how they are sitting on TiO2 fiber, for that we did TEM, and you can see this nanoparticle is well immersed on the surface of TiO2 fiber. So they have like good attachment with each other. Now, I mentioned already, UVV's absorption spectra is very important to do photocatalytic, any kind of photocatalysis, like from dye degradation to water splitting to make hydrogen. So for the powder A, this is simply a white powder. I didn't put any image for this one, but from this UVVs, you can understand it doesn't have any absorption in the visible region, which is starting from 400. However, when we go for silver gold alloy nanoparticle doped fiber, you can see how the color is changing depending on the nanoparticles. So this fiber is a pure TiO2 fiber. It doesn't have any kind of metal nanoparticles, so it's simply white. And the UVV spectra is this black one. I don't know if it's like clear. This black one. So it also doesn't have any absorption in the visible region. Now this one is the silver. So all these are reduced to make the nanoparticles. So this one is the silver incorporated nanofibers. It has some like plasmon band related to silver nanoparticle, and for the gold is related to gold plasmon band. And when we make them in alloy form, it has a very broad absorption in the visible region, which indicates it might be a good catalyst for solar light water splitting. Now, if we compare this catalytic property for production of hydrogen, you can see, as I mentioned, this has a very broad absorption in the visible region, and it doesn't have it. It can only be activated under UV light. So if you see the production rate, you can easily understand these are the good. This catalyst is better than the other one. That's why it's making higher amount of hydrogen when compared to this catalyst. Now coming to another two examples where we took perovskite, titanate perovskite base and tried to grow silver in situ silver nanoparticles. And like what is coming from UVV's absorption, when it's not reduced, it doesn't have any absorption in the visible region. And when we started reduction at 500 degrees centigrade, it started giving some absorption related to silver nanoparticles, but they are very tiny. That's why it's coming here. As we increase the reduction temperature, the absorption band is also, like the shape and the range of the absorption is also changing, as the color too. Now, this one is with cadmium sulfide on perovskite. And the same is concluded from the UVVs. No cadmium sulfide, doesn't have any absorption, and when it has cadmium sulfide, it's the yellow powder, and it started giving absorption in the visible region. Now, if you compare like the photocatalytic application, it showed very good hydrogen production rate. And also what we try to see if we use them like for kind of cycling application. So what we did, we irradiated, like we used that setup I have shown before. So we irradiated for 2 hours and collected hydrogen, and then we stopped the light and evacuate whole chamber to remove all the gas, and then again we start like the reaction for 2 hours. So we did like several cycles to see how it's giving, or how it's behaving for this kind of cycling stability check. And it showed very good cycling stability for like 12 hours for this material, and this one for until 8 hours for cadmium sulfide material. Like we could make it further because for the time constraint, but it proved that it's a very good catalyst for this kind of green hydrogen production. Now, I thought to put another example, although this is not related to green hydrogen production, but I thought to put this one because it might be interesting to some of you, as you are doing some like maybe functional group testing in organic chemistry. So what we did here is we made some that kind of nanomaterials which has these functional groups. So how we determine these functional groups? We did XPS, which might not be familiar with you, and also IR, of course, to understand what functional groups are here. So IR is the first one to identify the functional groups. So like as you can see, all these functional groups have some delta negative sites because they have like oxygen or nitrogen with their lone pairs. So what happened is that when we use this material for some kind of dye adsorption, we saw methyl orange and rhodamine B. I should put the structure, but sorry, my apology, I forgot. But you can check like the structure. So if you see the structure of methyl orange and rhodamine B, you can see these two are anionic dye. Like what does it mean? Because this dye molecule has like negative sites on their surface. Since it also has, like our nanoparticle also has negative sites, so it is not absorbing any methyl orange or rhodamine B. However, methyl violet and methylene blue, those are cationic dye. So what we saw is these are more likely to adsorb by our material. Even we did some mixed dye solution adsorption test. So what we saw is this one, this color you see, this is from like the mixing methyl orange and methylene blue. So when we did the like absorption and did UVB's absorption and took like UVB's absorption with time interval, we saw it's gradually absorbing methylene blue, but just leaving methyl orange in the solution. So this green color ended up with only orange, like yellowish orange color coming from methyl orange. So this seems very, very interesting. So I try to like give idea how we are working on this kind of materials field, and how we are making our materials, how we are exploiting their like properties for making either hydrogen or removing some dye. Even there is a versatile field, you can apply nanomaterials depending on their property. But maybe I thought to share some information with you. Those are like doing BSc and thinking how we can get involved in like research career. So maybe after BSc, like the suitable ways for university, like MSc in universities, and maybe all of you know like joint like about JAM, like that is for doing MSc in IITs. And also some of the research institutes in India, they they have their own admission test to allow students to get admitted in integrated PhD or even master's course. So just go and keep checking their web pages, like get information and prepare yourself. So after MSc, there are two ways. So what you can do, like what are those things? So you can go for PhD, so carry on research, or you can go for jobs. What is that kind of thing? So if you appeared for GATE, from your gate score you can get like you can apply for all these government and government undertaken companies for job. And also there are several like non-government companies, those are taking students for research purposes. But for PhD, you can there are like fellowships for doing PhD in like Indian universities and research institutes. Even even with GATE you can go for institute fellowship, and after junior research fellowship you can apply for these senior research fellowships for carrying out further. And like the important thing is, if you go for this option you have the chance to go back here after your PhD. And another thing I would like to encourage you to go and check is there are several like scholarships and fellowships in Indian government, like those are given to even I think from BSc, MSc, and PhD. So go and check this link if you can apply for a short like research work in other universities or some research groups. And those are intending to come to foreign labs. So there are several exchange fellowships that some university, like particular universities, they are also like giving that kind of opportunities by Indo like kind of collaborative programs. And also there are collaborative programs from Germany, France, US, and UK. So there are several more as well. So just go and check. So these I thought to inform all these things. But if you write this like keyword on Google, you might see some more options as well. And for that purpose, university and suitable research application with your CV, cover letter and short research summary. So I would like to like finish with this famous like quotes. Einstein said, play is the highest form of research. So if you play with your mind and chemicals while working in chemistry labs, you might end up with some outstanding result. So hope some of you can come for the research career in future. And finally, for acknowledgement, I would like to acknowledge my PhD supervisor and current supervisor here, all the group members, and EPS ESRC for funding. And thank you all for your time and listening to this talk. Hope I won't make you bored. If so, go for a tea or coffee. And I'm available here on emails and also LinkedIn, and I will be happy to take some questions and get connected with you later as well. And thank you.
Thank you, Srushi. I can see some of the questions here. So let them. Okay. So first question is, ma'am, I want to know about stability of gold nanoparticle or silver nanoparticle from Protein.
Right. Yeah. So as you see, like we made those gold and silver nanoparticles on the surface of some matrix. So those are socketed or made there. So those are very stable. And for that stability purpose check, I also run some stability, as I showed the cycling stability checks to see if we are losing some silver nanoparticles while we are doing the catalytic application. So those are really stable. Yeah. Once you grow on some matrix, those are really stable.
Yeah, can I just add a little bit more to this one, Rosie? Yeah, so if you just want to know about the stability of individual gold nanoparticles, silver nanoparticle, let's make it clear that gold nanoparticles are much more stable than silver nanoparticles, because silver nanoparticles have a tendency to get oxidized, whereas gold nanoparticles do not get oxidized easily. So that's why for in vitro applications and all those, mostly gold nanoparticles are being used rather than silver nanoparticles. Okay, Pratim. Pratim's next question was, what are the limitations of nanoparticles? Shreyoshi.
Right. Yeah, as like already you told about like the stability of the nanoparticles, that is the main thing. And when we are making or growing those nanoparticles, so we need to reduce like the material to make them in nanoparticle form. So the main thing is when you are reducing the nanoparticle, it can get agglomerate and make very big, not in a nano range. So it can make very big particles. So you have to be very careful while make those nanoparticles, and you have to design your like reaction so that you can end with proper catalyst. As I mentioned, when you are doing research, you have to think about all those things. And another thing is like when you are choosing some nanoparticles, you have to think about their oxidation tendency as well. As like they mentioned, silver is more prone to like oxidize, same as copper, iron. So when you are working with all those metal nanoparticles, you have to think about your application part, and you have to think about design your application like reaction as well, so that you can protect your nanoparticle and you can have like their benefit as well.
So next question from Shandular. Do nanoparticles conduct electricity?
Nanoparticles, I would say we use that kind of metal nanoparticle to make like insulating nanomaterial conducting. So I didn't present. I'm also working on electrochemical application as well, where we use that kind of conducting material to split water with like electrochemically. So for that purpose also, you have to choose proper like catalyst. Like we mainly work with like iron, nickel, or iron oxide, that kind of material. So electricity, I would say it's like electronic conductor or ionic conductor, basically. Yeah.
So Rama asked the next question. Can nanoparticles cause cell damage in case of medicinal applications?
Okay. Sorry, it's not like I'm not familiar with these things, but maybe if but
Huge
as far as I
research
know,
going
silver
on.
nanoparticles are used for like kind of biomedical application as well, and not biomedical, but as I mentioned, TiO2 is sometimes used for, always used for like your what it calls UV. Sorry. Sunscreen lotion, and you can also find that kind of nanoparticles like on some kind of medicine as well. So they can sometimes use for pigment reagent as well. So cell damage, I shouldn't say something on that part.
So nanoparticles are also being used for targeted drug delivery, right, nowadays. But let's make it clear that those things are also on research level mostly. So there are so many clinical trials and everything is going on. So we can't right now comment precisely about that.
Yeah.
So people are also researching on toxicity of nanoparticles, and that if even if it is doing the drug delivery afterwards, what is happening in the nanoparticles, how much percentage of the nanoparticles are going out of the body, or how much is there in the body, and if
Yeah.
there is any harm caused by those nanoparticles. So let's say that
And
right now that is under investigation.
maybe I would like to add a little bit more. There are some research for cancer treatment as well, like for the chemotherapy and all. People are trying to make targeted nanoparticles to destroy the cancer cell, and also
So any more questions? Okay, so please fill up the feedback form that we have shared in the message section. Uh, and let's thank Dr. Shreyoshi for the wonderful talk. I hope you'll again get Shreyoshi sometime. So with this, we would like to thank all the participants, and I would ask Mr. Biplav of our chemistry department to give the vote of thanks.
Ma'am, I am audible.
Yes. Yes, please.
Thank you, ma'am. I would like to take this opportunity to thank our esteemed speaker, Dr. Nonappa and Dr. Sreyoshi, for their excellent talks. We all have been enlightened today with different aspects of nanomaterial chemistry. Thank you once again. This webinar would not have been possible without active participation of all of you. So thanks to all the participants. Whenever we think of organizing such a webinar, we always get positive support from our GB President Sir, Dr. Joydev Haldar. Thank you, sir. We would like to express gratitude to our Principal Sir, Dr. AJ Hassan, for his constant support. We also like to thank our ITSC coordinator, Ms. Argha, academic chairperson, Ms. A. Moitra, for their constant support. Thank you all once again. That's it. Have a nice day. Bye bye and take care.
Thank you all.
Thank
Have a
you.
nice day. Thank you.